All right, so let's return to some notions of connectedness. So far, we've talked about what it means for a topological space to be connected, path connected, which is stronger. And now we would like to build up to something called simply connected, which means you don't have any holes in your space. And you have to define holes in a rigorous way. Really, I just mean low dimensional holes. You have to have some notion of what's the difference between a low dimensional and a high dimensional hole. But anyway, in order to do this, we're going to have to build up some new concepts. And these concepts are going to be based off things we've seen in the past. So I have a diagram here that perhaps you recall from one of the previous videos. And it kind of encapsulates the notion of deforming one function to another, right? So in this example, we were working in the space of continuous real valued functions defined on the closed interval from 0 to 1. We noted that was a path connected space because given any two functions, f and g, I can define a function that goes from g to f in a nice way. And this function, we then actually call a path. And so it's kind of weird because normally you think about a path as a continuous function whose starting point is like a point in your space and it ends at some other point in your space. And you say it's okay, it's like a path from x to y. Here we're saying h is a path from g to f. And that's okay, right? Topological spaces let us generalize and talk about paths between arbitrary points. In this case, our points are functions in a collection of functions. And okay, so we're able to do that. What we end up getting is if you plug in various values of t into this function h, it'll spit out one of these dotted red lines. If you plug in t equals 0, well, t equals 0 means you kill this term. This becomes just 1 minus 0 times g, so it's g. Similarly, if you plug in t equals 1, you get the function f, because this term gets killed. And if you go anywhere in between, so I have some examples here, for example, at time t equals 1/2, you're sort of like the average of those two functions. And so really what this is supposed to bring to mind is that you're deforming one of these functions into another, right? If you think about this happening continuously over time, right, these are minuscule little continuous changes to get from one function to another. And so it's kind of like you're deforming functions. What if we changed the codomain a little? It was nice above because we were working in the real numbers, namely these functions had codomain R. But okay, so you could have thought about these as paths in the real number line. F and G are themselves paths, and we found a path between them. But what if you changed R? What if you took paths in an arbitrary space? For example, a torus, which we write T2 sometimes. So if F and G were paths on a torus, and so I have, again, a drawing I just reproduced from one of the previous videos. Do you think it would be possible to deform F into G or vice versa? And here I've reproduced, okay, we are still thinking about I as the interval from 0 to 1, and that's representing time. And so you could imagine, okay, I have this path, and I have this other path. And you could think about them having direction in the sense that you're starting at F0, and maybe I put a little arrow indicating I'm traveling towards F1. For the purple path, it's a little weirder because it's a loop, so you can't really tell where you're starting and ending. But let's say I was traveling this direction, coming back that direction. So paths and loops can have directions. And the question is, can I continuously deform one into the other? And you should be able to convince yourself it's possible to go from red to purple. In particular, I mean, I like to imagine this purple loop as if I just took a necklace and draped it over a donut, right? And then this red loop is sort of the same deal. I kind of unclasped the necklace and draped it over the donut. But I could imagine taking the red loop, pulling the ends together, clasping it, right? Gluing is a continuous function. I'm allowed to do that. And then, gradually shifting it over and making sure it undulates in the right way that it overlaps the purple necklace. But then you have a question of, is it possible to get from this loop to this loop, from purple to teal? And so you think, okay, if I take this purple necklace and I shift it all around and maybe I bring it over one side, and how could I possibly wrap it around, right? And no matter how hard you try, you'll figure out it's impossible to do. You can't continuously transform purple into teal or vice versa. And really it comes down to that fact that the purple necklace was draped and the teal necklace is like a choker. It's like you actually wrapped it around the donut and then connected it. Like those are two fundamentally different things to do with a necklace, and you can't transform one into the other without, if you had a necklace sitting on your shoulder, how are you going to get it around your neck without unclasping it? But unclasping means ripping apart, and that's not a continuous operation. Okay, so those are fundamentally different loops in the space, whereas, maybe this red one and this purple one weren't so different. And in actuality, usually we're going to require that for two paths to be deformable into one another, usually we'll require that F and G have the same endpoints. I'm making the argument more generally here, and there are times when the more general case is useful, but it's generally much simpler if you're saying, okay, here's my path F, and all I want to know is, can I get from F to G? And G has the same starting point and the same ending point. That just makes it tidier to work with, and it does basically everything we would want the more general case to do. So we're going to talk about paths like that and how to deform one path into the other, assuming their endpoints are the same. So a little less general than this picture, but much nicer to work with. Okay, so let's define some terms. This is a big definition, but stick with me. We're given a topological space. We're given two paths. So again, I'm calling them F and G. They're defined on the unit interval, which we think about as time. And they're paths in X. X could be the real numbers. It could be a torus. It could be whatever topological space you want. And here I specify that condition where I want them to have the same initial point and I want them to have the same terminal point. Okay, so I go ahead and give the name P to the starting point. And so F of 0 and G of 0. At time 0, F and G are equal, so they're starting at the same point. At time t equals 1, F of 1 and G of 1 are both equal to Q, so they're ending at the same point. And we say that the path F and G are homotopic to one another if the following happens. Homotopic, I mean, homo comes from, what is it, Latin, I think, for same. And then topic, like topos, I mean, it has to do with topology in general, sort of talking about shape. But just think, they're really the same path, right? If you can deform one into the other in this way. If there is a continuous function, which is the deformation from one to the other, and instead of calling it a deformation, the formal term is homotopy with a y. So two paths are homotopic if there's a homotopy between them. And that homotopy is the function h with 4 properties. And this scares students the first time they see it. Remember, I is the interval, the closed interval from 0 to 1. But this looks kind of different from what I drew above, right? In this other example, this function lowercase h was sort of like a homotopy, but it was from the interval to the space, not the interval across the interval. So that takes a little getting used to. You can translate from one to the other. But the way people usually write a homotopy is this. So the interval across itself into your topological space. And it has to have the 4 properties outlined below. And again, these are not things you should memorize. These are things that once you sort of internalize what a homotopy is, you should just be able to write them down for free. It should seem natural, but the first time you see it, it's terrifying. So the way it works is easiest to explain with a picture. What we want to do is we want to take, some path f, some path g, and deform them into one another. Really, you can do this in either direction, because if you can deform forward, you can deform backward in time. And so those are what my 2 paths look like. So here's the point. Maybe I'll draw it in red. P is their initial point. Q is their terminal point. Remember, they share those, but they're allowed to do anything else in between as long as paths are required to be continuous, so they're not going to be broken lines or anything. And then the idea is, okay, same picture I drew before, right? After a little bit of time, I've deformed f that much, and then I deform it some more, and then I deform it some more, until I eventually get to g. All right, so that's our intuition, and these 4 conditions specify exactly that procedure. What you're going to want to think about is this first variable is going to be your x variable. The second variable is going to be time, your t variable. And so time is sort of measuring where we are along this procedure. So this was maybe t equals 1/4, t equals 1/2, t equals 3/4. At the end of your journey, you're at the function g. At the beginning, you are at the function f. And so you're thinking about time as what's happening during the deformation process. You're thinking about x then as the actual points on these paths. So we say that, let's focus on these last 2 properties first. We say that the initial point is always P and the terminal point is always Q. That's what that means. That means, yeah, if we're looking at kind of the starting point, so 0, then we want that to always be fixed here. We're not moving that around, right? We're fixing it in place. And again, you can define a more general notion of homotopy that allows you to move endpoints, but we're starting easy. Similarly, over here at this other endpoint, we want that to be fixed at Q. So that's what those final 2 properties mean. The first property then means, well, looky here. This is time 0. At time 0, your homotopy should be spitting out the function f. That's exactly saying, okay, time 0, I want my homotopy to produce the blue curve. Similarly, at time 1, I want my homotopy to spit out the yellow curve, the function g. So yeah, that's exactly saying I fix my endpoints. Whoops, I meant to highlight this. At sort of location 0, we're always at P. Location 1, we're always at Q. Time 0, we're just equal to the function f. Time 1, we're equal to the function g. And so if you can find such a continuous function, if you can find such a homotopy between your two paths, then those paths are said to be homotopic, which is just a formalization of the notion of I can deform one thing into another. And keep in mind, in some spaces, this will be possible for no matter what functions or paths you pick, like in this topological space. In other topological spaces, you won't be able to get from, in this case, G to H in a nice continuous way. So yeah, depending on your space, depending on the paths you start with, there may or may not exist a homotopy between them. And so that might make you think, oh, homotopies actually tell me a lot about the space I'm working in. If I could think, you know, if I know for a fact that there's a homotopy between any pair of points in the space, or any pair of paths in the space, I should have said, that tells me something. But you know, if there are some paths that can't be transformed into other paths, maybe they're like, maybe the space is like a donut. Maybe it has holes in it that I can't circumvent. Okay, and then our next comment notes that you can actually form equivalence classes from homotopies. So we call them homotopy classes, but really they're just equivalence classes of homotopies. So yeah, if two paths, F and G, are homotopic in your topological space, then they belong to the same homotopy class. So the homotopy class of F is written like you would write an equivalence class. It's the set of all things that are equivalent to it. In this case, equivalent, meaning homotopic. And I forgot to mention that here, but that's the symbol for homotopic. It's almost like isomorphic, but you leave off one of the equals bars and one of the horizontal lines. Almost like homeomorphic, I guess I should have said. People generally use the same symbol for homeomorphic and isomorphic. Anyway, that's what a homotopy class is. And so looking back at this example, I could say, well, let's draw a new example. I could say, you know, on a donut, and again, we want to fix the endpoint. And let's, for the time being, just talk about loops because they're nicer to draw. I could say this loop and this loop. Maybe I even cross over myself somewhere. Doesn't matter. I can continuously deform one into the other because they're just necklaces draped on top of the donut. So those are in the same homotopy class. Similarly, technically, there's the like constant path where you do nothing. You just stay at whatever point you started at and end there. That's also in the same homotopy class as those other two. If I wanted to talk about this guy, so there's some loop starting and ending somewhere. That's in a different homotopy class, right? I can't deform that to any of the other curves I drew, but it's in the same homotopy class as, say, this kind of wobbly guy. Right? You can continuously deform white into red or vice versa. And it's in the same homotopy class as, kind of running out of colors here, but let's just use blue maybe. It's in the same homotopy class as I could do like really wacky things. I could do this, could go all around, but as long as I circle once, I'm fine. Okay, it's honestly hideous, but yeah, you're allowed to like stray if you want. The only thing that matters for being in the same homotopy class is, do you fundamentally do the same thing? And in this case, the same thing means loop around that part of the donut. And you might think for a while about, are there any other homotopy classes? The answer would be yes. I can go around the like exterior loop, don't know why I drew it like that, the exterior loop of the donut, and you can't deform that into either of the other two types of loops. Okay, so that's sort of how you talk about homotopy classes, just what loops or what paths can be deformed into each other. And perhaps it's worth mentioning why this is an equivalence class. It's an equivalence class because, first of all, any path I draw, this is my function f, starting at 0, ending at 1, so it's a path, it's continuous. F is always deformable into itself. Trivially, I could do the like do nothing homotopy. Just leave everything where it is, don't deform it at all. So it is reflexive in the sense that every path is homotopic to itself. It's symmetric in the sense that if I know G, if I know I can deform F into G, then I could go in reverse. I could deform G into F. And it's also transitive in the sense that if I know F is homotopic to G, and then G can be wiggled a little bit into some function H, then so it shouldn't be too hard to convince yourself that, yeah, if you can deform F into G and you can deform G into H, then you can compose those two deformations, thereby getting a homotopy from F to H, which is the hallmark of transitivity. So it is really an equivalence relation. Perhaps next time I'll write down what it means to do some operations on these equivalence classes. But for now, it suffices to just say homotopies exist. They tell you a lot about space. And homotopy classes in particular are interesting objects to topologists. And yeah, I think we've seen enough examples just from pictures. So thanks for watching.